So this is a continuation from the last video, and where we last left off, we already finished with each of the element matrices. Okay, so I'm talking about this one and this one. Okay, so now we can assemble them into the global equilibrium matrix. So we have 6 displacements on this FEM model, right? The 6 displacements that I'm referring to is Q1, Q2, Q3, Q4, and Q5 and Q6. That's why we shall open a 6 by 6 matrix. Okay, and then 1, 2, 3, 4, 5, 6. Okay, so now we can assemble them. So here, all we need to do is just copy paste this into row 1 to 4 and column 1 to 4. Okay, so it should be simple enough. Okay, just like that. Let me rearrange this a bit. Okay, now let's take a look at the next matrix. So the next matrix, you have to be a bit careful because take a look at the heading of the column. It goes in the order 5, 6, 3, 4, whereas in the 6 by 6 matrix is in 3, 4, 5, 6. Okay, so what you should do is go through each row and fill in each entry into the global stiffness matrix. Okay, but the first corner is very easy. So here it says go to row 5, row 6, column 5, column 6. Okay, and then fill in 1, 0, 0, 0. So, okay, so easy enough. So these entries are done. Okay, now we move on to the other entries. This entry, right? These entries are for row 5, column 3, column 4, right? So let's go to there. Row 5, column 3, column 4 is minus 1, 0, right? Then this is row 6, column 3, column 4. So row 6, column 3, column 4 is 0, 0, right? Next we have okay, so this corner is done. Now take a look at this entry. So this is row 3, column 5, column 6 is minus 1, 0. So row 3, column 5, column 6 is minus 1, 0. Then what else do we have? Okay, this is done. The next one is row 3, column 3, column 4. Right, so this is 1, 0. Row 3, column 3, column 4. Row 3. Okay, so column 3 means plus 1 here. Column 4 means plus 0 here. Okay, then what else? Okay, so all of these are just zeros. So actually, even when you put them into the global equilibrium matrix, it will do nothing to it. Okay, but if you want it to be complete, so this is row 4, column 3, 4, 5, and 6, they're all 0. Okay, so you go to row 4. So 3, 4, 5, 6, they're all zeros. Okay, now, yeah, but that doesn't affect anything, so we can just remove all the zeros away, right? Okay, so now we can add in the displacement vector. So here, there's the displacement vector. Okay, so this is Q1, Q2, Q3, Q4, Q5, and Q6. And don't forget the load vector, or otherwise the force vector. So F1, F2, F3, F4, F5, and finally F6. Okay, so we can substitute in the boundary conditions. Okay, so what I mean by the boundary conditions, you look at the displacement of the nodes. Okay, so let me clean this up for a bit. So they want us to find the displacement of 2, right? So that means Q3, Q4 are unknown. But we know for sure that they're non-zero. Okay, they're non-zero. Now let's take a look at node 1. See, node 1 is fixed to the ground, right? Node 1 is fixed to the ground, meaning to say that it's unable to move. It's unable to displace horizontally. It's unable to displace vertically. So we know that the displacements both in the horizontal and vertical direction must be 0 for node 1. Therefore, we can conclude Q1 equals to 0, Q2 equals to 0. Now, take a look at node 3. Node 3 faces the same thing. It's being built into the ceiling, right? So it's not allowed to displace horizontally, okay? So it cannot move left and right. And it cannot also displace vertically. So it cannot move up or down. Therefore, we know that Q5 and Q6 is actually 0. Okay? So therefore, we shall substitute that into this equilibrium equation. So it should be 0, 0, 0, and 0. Okay? So don't forget that for the rows that have the 0 displacement boundary conditions, we can cancel the row and the corresponding column. So let's take a look at row 1, column 1, row 2, column 2. Okay, so same thing with 5 and 6. So row 5, column 5, row 6, column 6. Okay, so in the end, what we're left is rows 3 and 4. And here. Okay. So don't forget the factor outside, which is oh, I forgot to put the factor. There's supposed to be a factor here. EA. Okay, so don't forget this EA outside the matrix. Yeah. So at the end of the day, what you're left with is this 3, 4, 3, 4. Okay, should be 1 plus 1 over 2 root 2, 1 over 2 root 2, 1 over 2 root 2, and also 1 over 2 root 2. Okay, we actually know the forces acting, we actually know the forces F3 and F4. So what is F3 and F4? F3 and F4, okay, so I'm talking about this, F3 and F4, are the forces, the horizontal and the vertical force acting on node 2. Do we know them? The answer is yes, right? You see what the question say? They say they apply 1000 kilonewton force down on 2. So that means the vertical force acting on 2 is 1000 kilonewton downwards, right? In other words, 10 to the 6 Newton downwards. So how do we represent 10 to the 6 Newton downwards? Well, you go to here. Okay, so F4 is the vertical force acting on node 2, right? So you replace F4 with negative 10 to the 6. Let me go back down here. Here you replace it with negative 10 to the 6. The negative indicates downwards. Okay? Negative indicates downwards. Then F3 is just 0 because there's no horizontal force acting on F3. Okay? So we can calculate Q3 and Q4. So Q3, Q4 is equals to, okay, if you bring this matrix to the other side, right? And then you don't forget to bring this factor to the other side, so it becomes 1 over EA. Okay? Uh, okay, hold on. Let me get my answer. Yeah. So if you do your calculations, in the end, you should get 10 to the 6 over EA. So that's the first entry. And then minus 3.828 times 10 to the 6 over EA. Okay, that'll be the second entry. So yeah, that's how you do a truss element kind of problem. Okay, that's how you do a truss element kind of problem. So let me recap on how you do a truss element problem. Okay, so first thing you do is you model the problem, right? Every node has a horizontal and vertical displacement and horizontal vertical force acting on that node, right? Then for each element, you must write down the stiffness matrix, right? So it's a bit complicated because you have to choose a reference node. The reference node is the node that will help you decide what theta is. Okay, theta will help you calculate the value of L and M. Then you use that to find the entry of all the stiffness matrices here. Okay, so all the entries inside here that you see. So the first two column is the displacement of the reference node, right? Yeah, it is the displacement of the reference node, and then the next two columns is the displacement of the other node of the element. Okay, then once you're done with all the elements, you just assemble them into the global equilibrium matrix, insert the boundary conditions, and if there is zero boundary conditions, you can cancel the row, cancel the column, and get the reduced system to find whatever you want. So let's say here we want to find displacements. Yeah, and that'll be it. So it's not difficult, it's just really tedious. Yeah. But yeah, that's the beauty of it. It's actually pretty simple. So if you found this tutorial on FEM to be helpful, donate to me. You can consider donating to me on Payla to support the channel's growth. Thank you.